Hi, welcome to day 35, and today's episode is brought to you by a whole formula this time. You probably recognize this, A equals V squared over R. That's of course how you calculate centripetal acceleration, the inward acceleration if something is moving around in a circle. And what we want to take a look at today is the motion of charges in magnetic fields. And if a charge is moving through a magnetic field, it doesn't follow just any old path, it follows a very specific path. It's kind of like a projectile in a gravitational field. Not again. You're probably expecting that. Regardless, a projectile inside a gravitational field follows a parabolic path. A charge inside a magnetic field, it's going to follow a different type of path. Okay? And I'll give you 3 guesses, and the first 2 don't count what type of path it follows. But before we talk about the path that a charge follows inside a magnetic field, let's do a little review of circular motion. So if something is moving around in a circle, okay, let's say it's right there in the circle, the velocity is going to be tangent to the circle. Okay. Remember, it's always accelerating in towards the center of the circle, so that means the total force acting on it has to be in towards the center of the circle as well. In other words, the force acting on it is perpendicular to the velocity. Okay, so if you have a force that's perpendicular to a velocity, okay, you have something that is tending to move in a circle. Keep that in mind. Now, back to our charges moving in magnetic fields. So here's a scenario here. We have a magnetic field, okay, that's into the page, and it's denoted by all these X's. Remember, X's mean something is going into the page, O's mean something is going out of the page. So this magnetic field, it covers quite a large region. And here we have a positive charge Q, and it enters the magnetic field with some velocity V. And well, what's the force on this charge? It's a moving charge inside a magnetic field. It's going to feel a force. What's the direction of the force on it? So out comes the right-hand rule for the direction of a magnetic force. Thumb goes in the direction of the current, the way positive charge is moving, like so. Fingers go in the direction of the magnetic field into the page, and the force pokes perpendicularly out of the palm of your hand. So this thing is going to feel a force. In that direction, like so. Notice the force is perpendicular to the velocity, so this thing is going to want to move in a circle. So the next little while, it's going to be having a velocity tilted upwards, like so. Okay, what's the direction of the force on this thing now? So again, right-hand rule for the direction of a magnetic force. Thumb goes in the direction of the current, the way the positive charge is moving. Fingers go in the direction of the magnetic field, and the force pokes perpendicularly out of the palm of your hand, like so. And again, the force is perpendicular to the velocity. Okay, so again, yeah, you can see that this thing is definitely going to want to move in a circle. Okay, that is the key idea for today. If a magnetic charge, if it enters if an electric charge enters a magnetic field, it's going to move in a circle. Okay. And if you take more advanced courses, right now we have our magnetic field nicely lined up perfectly into the page. But if the magnetic field is going at some slight angle into the page, you learn in more advanced courses that instead of moving in a perfect circle like this charge, that the charge actually moves in a spiral shape like so. But for now, we're going to keep it real simple. We're going to be dealing with situations like this, and this charge, yeah, it's going to move in a perfect circle. So let's take a little closer look at what this means if this charge is moving in a perfect circle. Well, the force is perpendicular to the velocity. We know that from the right-hand rule. The charge is moving in a circle. Okay, so that means if it's moving in a circle, it's got to be undergoing centripetal acceleration. And the magnetic force, that's the force that's causing that centripetal acceleration. The magnetic force is the centripetal force. Okay? And remember what that acceleration and that force does. It doesn't make the charge speed up or slow down. It just changes its velocity. It just bends its path so it moves in a nice perfect circle. Regardless, the charge is moving in a circle. It's undergoing centripetal acceleration. The magnetic force is a centripetal force. So mathematically, what can we say about all this? Well, we can say, you know, the force is equal to the mass of the charge, or whatever that is, times the acceleration. The force is the magnetic force. And remember, the magnetic force in a moving charge, there's how you calculate it. QV be perpendicular. And that's going to be equal to the mass, okay, times the acceleration. And remember, the acceleration is the inwards acceleration. If something is traveling in a circle, it is always accelerating in towards the center of the circle. That is centripetal acceleration. So the acceleration is v squared over r. There's a nice little equation that will come in handy every now and then. If a charge is moving in a magnetic field, it's moving in a circle. There's the force on the charge, the magnetic force, and it's equal to the mass times the acceleration, which is v squared over r, this centripetal acceleration. We will come right back in a bit and take a look at a problem involving all this. Here's an example we want to take a look at. An ion with a velocity of 2 × 10⁵ meters per second enters a region where the magnetic field is equal to 0.1 teslas. The magnetic field is perpendicular to the velocity. The ion's radius of curvature is 15 centimeters. That's what's supposed to happen, right? An ion is an atom with all the electrons stripped away. It is a charged particle. If a charge enters a magnetic field, it starts moving in a circle, hence the radius of curvature. So the ion's radius of curvature is 15 centimeters. Find its charge to mass ratio. Now you might think, what an obscure thing to figure out, a charge to mass ratio. Okay, well, let me give you some historical perspective on the importance of that one. So here's something that we know. You've come across this number in a couple of examples we've done. The mass of an electron is 9.1 × 10⁻31 kilograms. Okay. Now the question is, how the heck do you figure out the mass of an electron? Like, you're obviously not putting the thing on a balance. Okay. Here's how it can be calculated, the mass of an electron. Remember last year we talked about Millikan's experiment? You know, he looked at oil drops suspended between charged plates. And Millikan, he found that the charge of an electron is equal to 1.6 × 10⁻19 coulombs. Okay, Millikan did that in the early 1900s. About, I think it was 20 years after that, a person named J.J. Thomson came along, and doing a problem, or by using a method that involves a calculation very similar to the problem we're about to do, okay, J.J. Thomson, he actually measured the charge to mass ratio of an electron. Okay? And again, the calculation he did was very similar to the one we're about to do. And think about that. If you know the charge to mass ratio of an electron, and you also know the charge, thanks to Millikan, then it's just a little bit math, and you can figure out the mass of an electron. So there's a bit of a historical perspective as to why what we're trying to figure out here really isn't all that obscure. Actually, when you look at the periodic table and you look at all the atomic masses, all those atomic masses were actually calculated with a calculation that's not a whole lot different from the one we're about to do. Anyway, so there's the problem. And of course, the first step in any problem, get all the information down on the page in a diagram. So here's a diagram, here's our charge. It's behaving like it's supposed to in a magnetic field. It is moving in a circle. The radius of curvature is 15 centimeters. The velocity tangent to the circle is 2 times 10 to the 5th meters per second. The magnetic field is 0.1 Teslas. And if you apply the right-hand rule the way I have this drawn out, you can see that the magnetic field is actually into the page, but really that's neither here nor there with regards to this question. You don't really have to know that. There's our charge, Q, we don't know what the charge is. There's the charge's mass, M, we don't know what that is. And what we want to figure out is the charge to mass ratio. What's Q divided by M? What else do we know about this situation? Well, remember, it's moving in a circle. That means it's accelerating towards the center of the circle. That means there's got to be a force acting on it towards the center of the circle. And that force, of course, is a magnetic force. And this video might have to stop because I can't get the marker cap off. Oh well. Okay. Regardless, that force, remember, is the magnetic force. Okay, so let's see if we can figure this all out. Okay, don't need this anymore. Okay, so what do we know about this situation? Well, we know this charge, it's moving in a circle. If it's moving in a circle, it's accelerating in towards the center of the circle. So the force is equal to the mass times the acceleration. The force, that's this thing, that's the magnetic force, right? And remember, if you have charged particles, you can ignore gravitational forces with respect to electrostatic and magnetic forces. So yeah, that is going to be the only force acting on our charge, the magnetic force, and it's equal to the mass times the acceleration. The magnetic force it's the magnetic force on a moving charge. There's how you figure it out. QVB perpendicular, and it's equal to the mass times the acceleration, and the acceleration is the centripetal acceleration towards the center of the circle, V squared over R. Now remember, if you're going to use this formula, the magnetic field has to be perpendicular to the velocity, and yes, it tells us right in the question, okay, that the magnetic field is perpendicular to the velocity, so we're okay there. And we are interested in the charge to mass ratio. Okay, so let's make this look like we want it to look. Okay, so let's get the M over the other side, and then it's going to go nicely downstairs underneath the Q like it's supposed to. Okay, let's take the B over to the other side, it's going to go downstairs. Let's take the V over to the other side, it's going to go downstairs. And we are going to end up with something that looks like this. Okay, let me just check my work. M goes over the other side, goes downstairs underneath the Q. V and B go over the other side and they go downstairs. So we've got a V squared left on top and R left on the bottom. Okay, perfect. This V is going to annihilate one of those V's. And there is your answer. The charge to mass ratio is going to be the velocity, which is 2 times 10 to the 5th, divided by the radius. Now remember, this is in meters per second. Change your radius to meters. So 15 centimeters is going to be 0.15 meters. And then we have the magnetic field, which is 0.1 Teslas. So you grind this through your calculator, and I believe you get, I worked it out here, 1.3 times 10 to the 7th units. We're talking charge to mass ratio. Everything else is in base units, so our charge should be in base units, coulombs, and our mass should be in base units, kilograms. There we go, 1.3 times 10 to the 7th coulombs per kilogram. And that's a reasonable answer. Again, if you're talking about atomic size particles, the electric end of things is usually way bigger than the gravitational end of things. So a really big number here, it kind of makes sense. All right, as far as an assignment is concerned, naturally, we'll post one to go along with this. Make sure you give it a shot. Okay, that's how to develop a real understanding of what's going on here. Make sure you finish it for Monday. Actually, to be perfectly honest, if you didn't finish it for Monday, that would be okay. Because Monday we're actually going to do a little more with regards to this kind of stuff. It's very qualitative, not a lot of math involved. There won't be an assignment to go along with it. So conceivably, you could finish this up on Monday. And also next week, Tuesday, you'll be getting a review sheet, and then test Wednesday, Thursday. Bye for now. Enjoy your weekend.